Talk y'all nah.
Say my name, say my name.
Marco Pereira.
Lorentz transformations, electromagnetic waves, and the hypergeometrical universe. From Maxwell's equations to 4D geometry and quantum coherence. Presented by Dr. Marco Pereira, creator of the hypergeometrical universe theory. I am teacher.
And one of the things that confuses me the most is what gravity is.
Gravity is the curvature of space and time, and you're moving on the curvature of that fabric. That's gravity. Matter tells space how to curve. Space tells matter how to move. It can't do anything else but do that. It's like you have a funnel and you take a ball and you roll it on the funnel. The ball can only do what that funnel tells it to do.
What is gravity? If you first thing you'll notice when you start thinking about gravitation is that if you pick up an electron and a proton, they will interact through electromagnetic fields. You are told that there is gravitational interaction, but there would never be an experiment that could detect the gravitational attraction between them because electromagnetism is so much stronger than gravity. If you allow the electron and proton recombine, you'll be left with just gravitation. If you are a scientist, the first thing you will do is to challenge the idea that gravitation and electromagnetism are distinct forces. The second thing you would do is to consider the ways neutral moieties interact. If they have dipoles, they will interact through dipole-dipole interaction. If they don't have dipoles, e. a hydrogen atom, then they might interact through change density fluctuations. We know that electrons zip around and collide with femtosecond intervals in metals. Perhaps there are fluctuations that are even faster, say fluctuations with the Compton period of a hydrogen atom or 4.056 times 10 to minus 24 seconds. What is gravity according to the hypergeometrical universe theory? Gravity is a van der Waals force where relaxation takes place at 4e to the minus 24 seconds. Van der Waals force is due to correlated charge fluctuations in a neutral moiety. What Einstein, Newton and all the other physicists missed in the absolute clock that the universe has and that who unveils. You might ask, is this a simpler model, other than creating a new force? The answer is yes. You might ask, does this create a force that is consistent with gravitational forces? The answer is yes. If it is a simpler model and if it is consistent with observations, that is the model a scientist should present and not general relativity. Tell that to Dr. Neil deGrasse Tyson. Simple derivation of the laws of nature. You can find the derivation in the Python notebook above. This is a 4D plot of two interacting bodies or charges. Let's call them body 1 and body 2. Remember that in who, there is an absolute reference frame and space is Euclidean. The vectors are really 3D vectors. We only see their profile. Each horizontal line represents a moment in absolute time and a value of the 4D radius. The vertical distance is c times the absolute elapsed time. The reason is because in who the locus of all particles is moving at the speed of light perpendicular to the hyperspherical hypersurface. For the calculation, one chooses to use delta t equals to r0 divided by c, so the vertical distance is also equal to r0. The spatial reference frame is such that at absolute time, I derived the forces in the absolute reference frame, r0 divided by c. The two bodies were connected by a vector r0, going from body 1 to body 2. So, body 1 is the center of reference, 0, 0, 0, 0, in this calculation. Body 2 is at vector r0 from body 1, the origin of the absolute reference frame. Body 1 will be at position 3 after delta t equal to r0 divided by c, and position 3 will be given by vector v1 times delta t. Body 2 will be at vector r0 plus vector version 2 times delta t. Notice that all this description is done in a single reference frame, the absolute reference frame. Fortunately, the absolute reference frame is equal to any reference frame that is not traveling at relativistic speeds. The reason is simple: all galaxies, and its components, are traveling at small idiosyncratic absolute velocities. The Milky Way is traveling at 0.2% of c. At this point, you notice that we don't need to worry about the difference in time. The difference in space tells us everything we need to know. You might complain that this picture is too simple. That would be poor reasoning, since a simpler model is better than a complex model. Maxwell's equations imply light as an electromagnetic wave. By the end of the 19th century, Maxwell's equations had formalized our understanding of electromagnetism. In vacuum, where charge and current densities vanish, these equations predict wave propagation. The electric, E, and magnetic, B, fields are coupled and obey second-order wave equations. From Maxwell's equations one can readily derive wave equations for E and B. Let's now look at how electric and magnetic fields transform when we change reference frames. To convert from one inertial reference frame to another, one just need to use this tensorial equation and Lorentz transformations. In modern physics, we unify E and B into a single 4D object, the electromagnetic field tensor, or Faraday tensor. This tensor captures the relationship between the fields in a way that respects the symmetries of spacetime. When an observer moves relative to a source of electromagnetic fields, the individual components of E and B will appear different. But what really happens is a 4D rotation, a Lorentz transformation, applied to the tensor. This mixing ensures that Maxwell's equations still hold true in the new frame. Importantly, this is something Galilean relativity cannot do. It doesn't preserve the structure of these equations. That's why Lorentz transformations are essential for electromagnetic theory. In the diagram, you can see how a Lorentz transformation maps the original field configuration, E, B, into a new one, E', B', while preserving the underlying physics. Why Galilean transformations break Maxwell's equations. Galilean relativity assumes absolute time and linear addition of velocities. Under a Galilean transformation, time remains the same and space shifts linearly. X prime is equal to x minus vt. T prime is equal to t. Applying this to the wave equation introduces extra terms, mixed partial derivatives. The resulting equation is not the same wave equation. This breaks the symmetry of Maxwell's equations. The speed of light becomes frame-dependent. Now let's look at what goes wrong if we try to apply Galilean relativity to electromagnetic waves. Galilean transformations assume that time is absolute, it doesn't change between frames, and that velocities simply add. This works well for classical mechanics, but not for light. If we apply a Galilean transformation to the wave equation derived from Maxwell's equations, we find that the transformed fields do not satisfy the same wave equation. In fact, mixed derivative terms appear, and the speed of propagation can change depending on the frame. This means that Maxwell's equations are not invariant under Galilean relativity, they actually get distorted. The electric and magnetic fields no longer behave consistently, and most importantly, the speed of light would no longer be constant across all inertial frames. That's a big problem. It contradicts the vast body of experimental evidence, including Michelson-Morley. That's why we needed a new transformation, the Lorentz transformation, that respects the structure of light propagation. The diagram illustrates how a nice sinusoidal wave in the rest frame becomes distorted in the transformed frame if we use Galilean relativity. You might ask, where is Lorentz transformation and the hyperbolic spacetime? These are Lorentz transformations. Notice that x prime and x are related by gamma. The same goes for t prime and t. The extra term only adds a shift. What is important is the factor on t and x. That factor is gamma. The other term is always a shift. It is useful if you want to create sophismas and fool yourself in Gedanken experiments. In other words, the derivative of t prime with respect to t is gamma. If you want to find out time dilation, you just integrate it and the time dilation will be given by gamma times delta t. The same will happen for the space dilation. You never hear about space dilation because in Einstein cult we talk about length contraction and go on and on trying to figure out how length is contracting, etc. It is idiotic. The reason is that the laws of nature should not be dependent upon the reference frame. The physics should be only one. In other words, by saying that length of an object is contracting, one introduces a new virtual force to do that job. So, the physics becomes dependent upon how you look at reality, and that is a poor model. Here you can see the rotation matrices for velocities along x. In other words, Lorentz transformation is a rotation by an imaginary angle, c cos alpha equals gamma, and the sin alpha equals beta gamma. This means that instead of having cosine of alpha squared plus sine of alpha squared is equal to 1, we have hyperbolic cosine of alpha squared minus hyperbolic sine of alpha squared is equal to 1, with hyperbolic tangent of alpha is equal to v divided by IC. Notice that in Minkowski spacetime, the time coordinate is ICDT instead of just CDT. If we choose to use the time coordinate as CDT instead of just ICDT, then the hyperbolic functions become real functions. Here you can see the rotation matrices for velocities along y and z. Here you can see what I mean by rotation. Well, before me, Minkowski explained Lorentz transformations as rotations in spacetime. I explained that the rotation really happens in the 4D spatial manifold. Spacetime is just a representation where the absolute time is presented as a radius. This has a physical meaning because the locus of all matter in the universe is expanding at the speed of light. One might ask why there isn't any dispersion for the matter distribution along the radial direction. The reason is simple. All particles surf the inner dilation layer or IDL, a remnant of the Big Pop cosmogenesis. The inner dilation layer is a hyperspherical metric wave propagating outwards at the speed of light. Notice that propagation around the hyperspherical universe is akin to surfing the inner dilation layer, and that is exactly what Newton's laws of dynamics tells us. Local homology of L. The local homology between the light-speed expanding hyperspherical universe or hypersurface, L, and Minkowski spacetime becomes evident when considering small distances. The curvature of L appears linear, matching the flatness of Minkowski spacetime locally. Notice that who brings Lorentz transformation to both 4D spatial manifold and the 4D spacetime. In science, small conceptual changes are relevant. In standard special relativity, there's no way to identify an absolute rest frame, motion is purely relative. But in who, we add one more spatial dimension and envision the universe as a hyperspherical hypersurface that expands at the speed of light. All particles surf this expanding shell, the inner dilation layer, and move at speed c along the radial direction. That direction becomes our preferred, absolute axis, perpendicular to every point on the hypersphere. This reintroduces the idea of an absolute reference frame, not as a violation of relativity, but as a geometrical truth of the higher dimensional structure. Now, Lorentz transformations are simply rotations within this 4D space, and we can visualize them clearly using cross-sections. Now let's zoom in on a cross-section of the 4D hyperspherical manifold. It's a 2D slice that includes the radial direction and one tangential direction. In this view, particles travel along the radial direction at speed c, while their apparent motion in the tangential direction, from our 3D perspective, gives rise to what we interpret as velocity v. The rotation angle alpha in this cross-section is directly related to the boost velocity. Hyperbolic tangent of alpha is equal to v divided by c. This is the geometrical root of Lorentz transformations. The stretching of space and time is visualized as the projection of motion from the boosted frame onto the absolute reference frame. The brilliance of the Who model is how cleanly it transforms the abstract algebra of relativity into pure geometry. We now see that applying a Lorentz boost to both wavelength and period conserves their ratio, preserving the speed of light. We all know that Lorentz transformation is a rotation in 4D spacetime. Here is the Lorentz rotation matrix. Galilean covariance or Galilean transformation between two inertial reference frames is just a translation where x becomes x plus a, and t becomes t plus b. What did all scientists miss about Lorentz transformation? We all know that the Lorentz rotation in spacetime preserved the electromagnetic wave equation. Once we realized that, we forgot all about waves, and focused just on space. Minkowski introduced the spacetime paradigm and the Minkowski metric. Later, Einstein deformed the metric to fit whatever he wanted to fit. That was a mistake. There was important information on the concept of waves. We know that whatever you do to spacetime, you are not changing the wave. In other words, the peaks of a cosine of kr will always happen at kr equal to n times 2 pi. This picture depicts a wave. In other words, whatever Lorentz rotation does to spacetime, it must also do to the k-vectors such that kr is conserved on all reference frames. Let's now look at the wave equation from the Who perspective. In a 4D spatial universe, wave propagation is described as sin k dot operator r. To preserve phase under transformation, both the wave vector and the position vector must transform consistently. That requirement leads to a very elegant condition. K equals k. Here, M is the Lorentz boost matrix in the 4D absolute reference frame. This means that both the wavelength and period are stretched by the same Lorentz factor, and so their ratio, the speed of light, stays unchanged. This isn't just a mathematical trick, it's a consequence of the geometry of the Who model. It shows why light speed is invariant across inertial frames. We're no longer appealing to the invariance of Maxwell's equations as an axiom, we're seeing it emerge from 4D geometry. This is where the Who framework becomes predictive and powerful. Rather than using the classical principle of least action, Who replaces it with something more fundamental, the quantum Lagrangian principle. This principle states that a fundamental dilator, a particle, will only follow trajectories where it remains in phase with the surrounding metric field, or dilaton field. Since the wave is described by a phase sin, k dot operator r, the QLP ensures that physical motion corresponds to the directions where interference is constructive, where the wave remains coherent. This idea, combined with the transformation condition k, m equals k, allows us to derive the laws of motion, not assume them. That includes classical mechanics, electromagnetism, and gravitation, all emerging as consequences of 4D coherence. Let's bring everything together. In the WHO model, space is not 3D, it's 4D. And this 4D hypersphere expands at the speed of light. That's not just poetic, it has consequences. Particles don't drift arbitrarily, they surf a very specific geometric surface, the inner dilation layer, always at speed c in the radial direction. This gives us a built-in absolute frame, rooted in the universe's topology. It makes Lorentz transformations obvious, just spatial rotations in this 4D manifold. Most importantly, wave behavior fits naturally. The reason the speed of light stays constant isn't because we impose it, it's because both wavelength and period are stretched equally by the geometry itself. And from that, using the quantum Lagrangian principle, we derive physical laws, not by minimizing action, but by preserving phase coherence in the absolute frame. This is what makes WHO a new foundation for physics. Let's take a step back. What WHO gives us is not just a new interpretation, it gives us a new foundation. Instead of patching together relativity, quantum mechanics, and field theory, WHO starts with geometry and lets the rest emerge naturally. The speed of light doesn't need to be declared constant, it must be constant, because of how space and time stretch in 4D. Lorentz transformations are no longer mysterious, they're just rotations. And the quantum Lagrangian principle takes us even further, into dynamics, structure, and beyond. The hypergeometrical universe reframes our entire understanding, and it's just the beginning. Einstein's special relativity. The one and only thing Einstein did in his special relativity was to materialize spacetime and use Lorentz transformations not only for the trajectory of photons but also for the trajectory of inertially moving material bodies. Dr. Einstein should have realized his theory was wrong by the time he discussed the twin paradox. Einstein's general relativity. Now, let's discuss what Einstein did in his theory of general relativity and its implications. Minkowski spacetime reality. Einstein took the concept of Minkowski spacetime and made it a physical reality. When we use a spring model to describe small deformations in a bridge, we don't literally think the bridge is made of springs. It's just a useful model under certain conditions. Similarly, Minkowski spacetime, which incorporates Lorentz transformations, was a useful mathematical concept for describing local gravitational interactions. Mistake of Minkowski spacetime. However, treating Minkowski spacetime as a physical reality was a mistake. Instead of viewing the universe as an embedded, light-speed moving hyperplane in a 4D spatial manifold, Einstein maintained a 3D universe and made spacetime a tangible entity. This decision was flawed. Minkowski spacetime error. Minkowski spacetime, with built-in Lorentz transformations, was useful locally but inadequate for describing the entire universe. Einstein's general relativity succeeded locally but failed to provide a comprehensive model of the cosmos. Local homology between L and Minkowski spacetime. There is a local homology between the light-speed expanding hyperspherical universe topology, L, and Minkowski spacetime. For small distances, L S curvature appears linear, mirroring Minkowski spacetime. I calculated both the force exerted by body 2 on body 1 and the force exerted by body 1 on body 2 to make sure Newton's third law of dynamics was still valid in this absolute reference frame formulation. It is valid. General formulation of Lorentz transformation. Here, we introduce the projector P of V. 1 is the unitary matrix. 1 minus P of V is the part of a vector that is not in the direction of V. Notice that only vectors along the velocity direction are affected by Lorentz transformation, relativity. Anything perpendicular to the direction of motion is not. This is the most complicated step. Everything else is just simple algebra. Definition of the projection operator and an example of projection. The hat symbol stands for normalized or unitary vector. The exception is when we introduce the verses for forces. There the vector is not unitary, just for a normalized vector with respect to r0, the scaling parameter. This derivation showcases what happens in the K-space. Notice that the indices 0 are used for the absolute reference frame and 1 for an inertial reference frame with velocity v. Equation 54 expressed exactly that idea. K1R1 is the k-vector in the universal reference frame 1 times the position within that same reference frame. The result is a number, and that number is equal to the same number calculated on the absolute reference frame 0. Going from the reference frame 0 to reference frame 1 is the same as rotating R0 by matrix M. If one rotates R0 by M, one can calculate how the k-vector have to change such that K1R1 is equal to K0R0. That is presented in equation 58. This is the Python code showing the vectors v_1 and v_2, as well as the vector r0_. Vector r0 is the scalar or scaling factor associated with this interaction. You can also see the Lorentz transformations m1 and m2, expressed in terms of the projection operators for directions v1 and v2, and the corresponding gammas. Here you can see the rotations m1 and m2, the vectors v1, v2, r0_. Vect, the scalar r0, the speed of light c, and r1 and r2. R1 is really r14 in the drawing, and r2 is r23. R1_hat and R2_hat are just R1, R0 and R2, R0. R0 is the scaling factor. Notice that R1 and R2 are vectors. In other words, the nomenclature can always be improved. Notice the addition of an x*r_hat, where r_hat is the versor for the acceleration and force. Hat is used as a normalization symbol for the velocity, for r0. For all the other vectors, hat means scaled by r0, vector divided by r0. P1 and P2 are the normalization factors for R14 and R23. Notice that x*r_hat is the sideways step the fundamental dilator has to do to satisfy the quantum Lagrangian principle. It affects the distance r23, a r2. In other words, the acceleration or force will be given in terms of r23. For it to be the absolute force, it has to be written in terms of r, or the radial direction, perpendicular to our 3D hypersurface. Hence, this explains why after the calculation, one still have to multiply it by Dr. 23, drive. Notice that the amplitude of the force acting on body 1 and 2 are the same. How the k-vector were rotated. In slide 10 we derived the rotation of the k-vector. This is an important aspect for the hypergeometrical universe theory. Einstein's model didn't have an absolute time or a cosmological clock timing interactions across the universe. You might think that that is a problem, but in fact it saves us from the embarrassing situation where we say phrases like this: neutrinos don't interact with hadrons because they have no quarks. Or they don't interact through the strong force. This might sound profound and mysterious, but it is really dumb and obscure. Who just says, neutrinos don't interact other than at close range because they have the wrong frequency? Here I am stating frequency not in the idiotic New Age way but as in, tunneling frequency. Neutrinos have a different tunneling frequency, and because of that its interaction with other particles lead to inconsequential beatings. Imagine you are a fundamental dilator interacting with a neutrino. You are positive now, and you feel attracted to the neutrino. In your next phase, the neutrino might be positive and you are still positive, so you will be repelled by it, etc. That is what I mean by beating. How the k-vector were rotated. In slide 10 we derived the rotation of the k-vector. This is an important aspect for the hypergeometrical universe theory. Einstein's model didn't have an absolute time or a cosmological clock timing interactions across the universe. You might think that that is a problem, but in fact it saves us from the embarrassing situation where we say phrases like this: neutrinos don't interact with hadrons because they have no quarks. Or they don't interact through the strong force. This might sound profound and mysterious, but it is really dumb and obscure. Who just says, neutrinos don't interact other than at close range because they have the wrong frequency? Here I am stating frequency not in the idiotic New Age way but as in, tunneling frequency. Neutrinos have a different tunneling frequency, and because of that its interaction with other particles lead to inconsequential beatings. Imagine you are a fundamental dilator interacting with a neutrino. You are positive now, and you feel attracted to the neutrino. In your next phase, the neutrino might be positive and you are still positive, so you will be repelled by it, etc. That is what I mean by beating. The k-vectors for the dilator field are trivial in the framework of the moving object. In other words, if you are a body in motion, the dilaton field you are creating will look spherically symmetric in your reference frame. I applied the quantum Lagrangian principle in the absolute reference frame, so I need K1 and K2 projected into the absolute reference frame. Here we have the simple algebra that relates k-vectors in different reference frames. Equation 68 shows the simplicity of the k-vector in its moving reference frame. It will appear deformed in the absolute reference frame. Just to emphasize, instead of being ignorant of the underlying clock process, the fundamental dilator tunneling, and paying attention only to m time r, modification of the metric, who uses the absolute reference, the cosmic clock, and derives the laws of physics using the effect of Lorentz transformations in the reciprocal space, k-space. Needless to say, who simplifies physics. Instead of monkeying around with arbitrary metrics, arbitrary guesses, who derived laws that can be used in an Euclidean 4D space. So, it is trivial to derive gravitational Poynting vectors and the total irradiated gravitational field. Einstein also made a mistake in that derivation. Occam's razor demands the simplest possible explanation for all phenomena. Simple definitions of the dilaton field and the application of the quantum Lagrangian principle. Notice that for the field 1, the derivation of the denominator, envelope, should be 0. That is the reason one didn't just mindlessly followed the derivation of the ansatz. Remember, this is a simple derivation that should use physics for guidance. For the field 2, one uses the large N approximation. Field 2 is created by n fundamental dilators, and that will create an interference pattern where the oscillations will seem too close. For that reason, I considered the cos nkr to be 1, since the fundamental dilator will always find a peak close to it. It will always join the peak that minimizes space deformation. In the case of two charges with equal sign, the closest peak will be the one that moves them away from each other. For opposing charges, the peak will bring them closer. Numerically, physically these peaks will be indistinguishable. Previously we derived the grand unification equation for static interacting bodies or charges. Here we do it again, now without the constraint of being static. The derivation was done in a 4D spatial manifold, where the universe is a dynamically moving, lightspeed expanding, hyperspherical hypersurface. The calculation comprises the calculation of the derivatives of fields 1 and 2 to calculate x, or r. The Python code replicates the calculation described in prior slides. Here, we calculate the derivative of phi_1. The final result. This is an extra factor that multiplies the empirical laws of nature with which we are familiar. Laplace and the instantaneous speed of gravitation. Notice that the dependence is upon instantaneous distance, as gravitation has traveled from the Sun to the planets while the planet traversed a distance v1 r0 c. The reason is that gravitation is carried by the dilaton field, which is always on. So, the gravitation planets are sensing right now, which was created r0 c seconds before, where r0 was the distance at that time. Radar measurements give distances to planets. At the time of the emission, the distance was r0. Light traveled, r0 plus v1 r0 c, bounced on the planet, and returned, traversing twice that distance. That is how a distance is measured, which is the definition of p2. This puzzled Laplace that the law of gravitation would depend upon an instantaneous distance. This led him to consider that gravitation was instantaneous. Hey, can you show that this is correct? Of course, here are Who predictions of planets' perihelion precession rates showing that Einstein got it wrong on Mercury. In other words, Who makes better predictions than GR? Notice that the force calculated on a body 2 or 1 is the same, Newton's third law of dynamics. That is possible because the forces are always expressed in the absolute reference frame. These are the references. Papers in Zenodo. GitHub repositories with papers and Python notebooks. Papers in Zenodo. Here are the 3 papers. The Hypergeometrical Universe. Who the Big Pop Cosmogenesis. Anyone is welcome to write a comment, critique, or praise my work at preprint. Org or Zenodo. Org.